So it's my pleasure to introduce Taylor Hayward. Taylor works at Apeel Sciences, sorry. And this is an agricultural technology company, and they focus really on the prevention of food waste. Today, Taylor will speak to us about the use of volatiles and analyzing them through GC-GC, specifically for fruit. And for me, it's a really exciting topic because I really like the idea of using volatiles as a tool to solve a problem. So I think it's will be a great talk, and the floor is yours.
Thank you very much. Good morning. I'm really excited to talk to you today about how we're using GC-GC at Apeel. Want to start by saying thank you to the organizing committee here. It's been a wonderful show so far. I'm really impressed with all the work that's going on. Really excited to see how far along LC has been taken, and I can't wait to use it one day in the lab. But until then, we'll be using GC-GC. So for today, I'll talk about Apeel as a company, and then how we are bringing GC-GC into the lab, which kind of fits really well with some of the discussions from the group yesterday. And then we'll talk about like how we're actually using it from untargeted to targeted analysis. Okay, so Apeel as a company, our mission is to work with nature to improve access to quality produce and reduce waste to ensure an abundant future for the planet. How we do this is by using food to protect food. Our products are made of plant-derived materials that we can put onto produce that doubles the shelf life of them. So we're hoping to reduce the amount of food waste and maybe even access quality food to more remote kind of areas. So this is basically what we have here. So just kind of showing pictures of what our product does. We have one side is without Apeel, so this is your normal fruit, and this is a time-lapse video if it goes. And on the other side, we have the Apeel treated fruit. Oh no, it keeps stopping. Oh, here we go. Because it's really actually really powerful to see side-by-side comparisons of our treated fruit with the untreated fruit. And what you can see is, you know, our treated fruit, it stays firm, it stays kind of big and moist, and the others start to shrivel and decay. These are all just held out at ambient temperatures, so it's just kind of sitting on a shelf. We have this camera that just kind of moves along and takes pictures at every certain intervals, then we stitch them all together to produce these time-lapse videos. And we've tried this on dozens of different types of fruit with all very similar kind of outcomes, where you see the Apeel treated lasting a lot longer. And so how this works is we basically just keep moisture inside and oxygen outside. And so you'll see a lot of avocados. This was our first produce category that we the market with. But getting more into kind of what we do in the analytical lab, we do all sorts of things. We span the entire business, going from our formulation development to our quality control, you know, raw material, manufacturing release, that kind of thing, to how it works on produce, and then kind of going along that way. So fruit quality is really important to us. And so we can use conventional means to measure different kind of attributes, such as firmness. So we have like this little tool that can measure how hard or soft your avocado is. We can use a lot of pictures to show either inside or outside quality. And we also use things like sensors to measure CO2 or respiration. But we also have our analytical lab, so GC-MS, and so we've done, you know, conventional analysis to look at things like vitamin E, and LC-MS to do things like vitamin C. We also do a lot of fatty acid methyl esters, and so here's some of the outcomes of some of our tests. So looking at omega-6 and 3 ratios in avocados, you really see, yeah, that treated and untreated really behave very similarly. Looking at the vitamin E and C interactions, these are synergistic. So as one goes up, the other goes down. But really the overall outcome here is that there's no real significant difference between the treated and untreated groups. So this is really used to confirm that the avocados are maturing normally. They're just lasting a whole lot longer. So this is great. So you can still eat your apple and keep the doctor away. But we're working with fruit. They're really complex systems. So this kind of gears towards a very comprehensive solution for measurement. So this is why we started looking at GC-GC. So our idea here is, really use this advanced technologies to understand more about what's going on with the fruit so that we can have a competitive advantage in measurement. So how we got it to the lab was, well, previous to Apeel, I was working at Dow Canada, and we were working with the reverse still flush flow modulator. So this was kind of our first area of entry. I'd used it before, so we thought to bring it and build it at home at Apeel. So we gathered up all the parts, and some of the most important ones were things like this, where we had this plate at Dow, and it was plugged, so they sent it to us, and it was really a way that we could connect our PCMs to a valve to the flow plates. And so what really hurt, probably more emotionally, was cutting this modulator so that we could then connect everything, but it works, so that's great. Now we have to find the right applications. So when we look at avocados, we know that they have a high oil content. This is the good fat. This is why they're that part of that superfood. It's composed of, saturated, polyunsaturated fats, but mostly monounsaturated fats. And so this is a good application for understanding more about maturity and ripeness of the avocados. And so we went to do some FAME analysis. So we went with this setup, which was the polar, non-polar. I really like this one. It's, separates by carbon number, and then as you go down in the chromatogram, it's that number of double bonds. So it looks really slick. You can get really good separation between the cis and trans isomers. So we went ahead and started to do a whole bunch of avocados this way. And this is some of the results that we get. So when you ultimately eat an avocado, the oil content or the monounsaturated fats is about 70%. But what we would see is that when these were really firm and hard, they were just slightly less than that. And then at different periods of time in the year, you can see that they even go lower. So what we're actually seeing is this is more later in the season, this August, September area. And what's probably happening is that they're just picking really early so that they can fulfill kind of orders and things like that. But this is important for us because now we see that these are a lot less mature than what we are normally receiving. So we might have to adjust formulations and things like that. Further, we can look at different countries of origin and what we saw there. Maybe a little bit, again, less mature fruit coming from Peru because it does have to travel such a long distance and things like that. But ultimately, GC-GC was a little bit too much for this kind of application. We started running through a lot of avocados, and so we needed a lot quicker, faster, higher throughput, so we ended up going back to one-dimensional GC. So now again, we're trying to find the right application. We see a lot of flavor analysis and things like that in the GC-GC world, and we're seeing a lot of applications coming from everyone here, basically. And so we started to do some volatile profiling. And we really were just kind of learning how to do SPME and apply this to GC-GC. All we had is a GC-GC FID, so we didn't get a lot of information. We went to this non-polar polar setup, but we could see that there's a lot of complexity there. And so this was really interesting to us, but we didn't quite know what to do with it. So, as we're trying to go, okay, well, let's, buy a commercial instrument, this wasn't going to jive. So we then went to a product demonstration with Sepsolve in Canada, and we had a different application which was looking at latent infection detection in these avocados. So what latent infection is, and what you can probably see it as, is sometimes when you cut open an avocado, they have like this little brown spot up at the stem. So this is a fungus that comes from the tree, gets into the fruit, but doesn't really start to present itself until the fruit starts to ripen and mature. And so we wanted to see if we could use volatiles to actually detect what's going on in the inside. And so we were able to infect some avocados. We had our control group as well, and we went up to Sacramento to use some thermal desorption tubes and just start to collect volatiles on these tubes. And then we sent them up to Matt Edwards and the team up in Canada. And they came back with this pretty chromatogram. So again, super complex. And in all honesty, I was hoping to like have that one peak pop out and be like, oh, yay, this is infected. That wasn't quite the case. Maybe if you squint real hard in the red box, you can see a little bit of differences. And so because we didn't see that one specific spot, we started to do more complex chemometric analysis. And this is where we started to use Chrome Compare Plus. And so this fits really well with the data that we got from the left side, and we can just plug it right into the right side and start to do some principal component analysis. And we start to really group and separate these things apart. And this is great because now we can actually understand and label some of these compounds of interest. And so this was big for us. And now we could put the pieces of, the really complex sampling, the separation, and then finally the data analytics. And so this is what resulted was we were able to kind of piece this together. So we have our sampling is basically going to be SPME or thermal desorption. Then we use flow modulation, and then our benchtop time of flight. We basically just are sticking with this one condition of non-polar polar column setup. I'm seeing a lot of this polar non-polar, which is actually really interesting, showing a lot of good results. But this is basically what we stuck with. And it'll work for a good majority of our applications. So this is basically our one setup to rule them all. So finally, we'll get into some of the actual applications and what we're using. And so why do we want to look at volatiles? So this is kind of going back to Apeel's mission of working with nature. Well, how does nature use volatiles, or how does nature assess quality of produce? The first you can think of is vision. So fruit are vibrant colors. It attracts animals to come eat them. And where we can use this is things like spectroscopy, hyperspectral imaging, and we can use those spectra to model quality metrics. And this worked out really well for us. So we used, this was a multi-year, thousands of avocados, multi-group kind of application where we were looking at near IR and being able to predict when fruit was going to be ripe. So we just came out with this product. Hopefully you'll see it we're going to try to see it in grocery stores so that you could put your fruit on there and it will say, enjoy your avocado toast tomorrow, or hopefully you're planning a guacamole party on Friday kind of thing. And so that's one way that we use the spectroscopy, but the other is looking at smell. And so fruits have like emit a smell, aroma to attract animals, but you can also kind of understand some of the quality attributes with the smell as well. And so this points really well towards things like gas chromatography. It's complex mixtures, and so we're looking at SPME and thermal desorption for our sample preparation. So really what we're trying to do is pair this comprehensive technique to ultimately lead to some kind of sensor type development. Really, the comprehensive technique helps us really fundamentally understand what's going on so that we can kind of move forward. So we start out with this untargeted approach, and it's really, figuring out what is of interest. Is there something there? And maybe even provide a little bit of ground truth for modeling aspects. From there, we can then hone into more targeted analysis, where we identify compounds of interest. Maybe we can select some sensors if there's just one or two, or maybe we can kind of start to establish thresholds and things like that. Then it's getting into the product development, where we are looking for rapid, high throughput techniques for more in-field deployment. So I'll show a few applications of where we started to look at this. The first is, there's a couple more, and shameless plug here for a couple of posters that we have going on in the upstairs with cherries and bananas. But yeah, so we'll talk about the ripening of avocados. So what we're really trying to address here is the current ripening process. And so we've been working really closely with a distributor in the Netherlands, and they have their ripe masters. And basically what they do is bring in incoming avocados. They'll take an initial measurement of things like dry matter, and then they'll put them into ethylene chambers to ripen them to get them ready for grocery stores. And based on what the incoming measurements are, they'll prescribe a set number of days. And this isn't an exact science, it's very much an art form. And so it's like, okay, well, you can do it, 2 days or 4 days or something like that. But ultimately what they do is after that time, they'll take some out, quality check, use a penetrometer, so it's a destructive test to measure their readiness. And then they will unload the room. But those that aren't really ready, they might either put them back in the room and ethylene and ripen them more, or it might actually even just go to waste. And so we thought, well, is there a way to actually measure this and monitor this so that that doesn't happen? And so we looked at things like spectroscopy, but also volatiles. Early on, we had done some experiments with SPME and GC-GC-FID, where we looked at kind of the avocado pulp that goes as it ripens. And what we see is actually when we can make our groups over the template, or we make the template and we quantify based on these groups, we see actually trends of these different functional groups, such as alcohols, decreasing over time, which is actually a lot different than, if you look at individual components as they go along. And so this taught us to think, well, maybe we can use some kind of sensor or something like that, like an electronic nose. These electronic noses have different kinds of arrays of detectors to look at functional groups. And so we thought maybe this is kind of that application. So we can measure our firmness of avocados and then hook up our electronic nose and just take sniffs every once in a while. And we can start to model the various stages from our sensors. And so we can, group them into things like firm, ready to eat, and then ultimately ripe. And so we're hoping to maybe use this in some kind of continuous monitoring phase. And so we're just still really building out the model, and maybe we can hone in and make it a little bit tighter and things like that. The next is in product quality, so understanding and monitoring fermentation in mangoes. Mangoes are tricky, and again, working with our group in the Netherlands, they receive mangoes from South Africa and the Dominican Republic, and honestly, we don't really know what the history of these mangoes are. Sometimes they're picked real early, sometimes they're a little bit later, sometimes they're waxed, sometimes they're not, and it really, that initial treatment and kind of understanding what's happening early really affects how our product performs. Because if we apply this barrier, we're a gas diffusion barrier, if we start to lower the internal oxygen within that mango, it'll start to ferment, go anaerobic, and taste terrible. So we want to make sure that we don't do that. And so we want to be able to measure, quality or attributes that are incoming. So how we did this is we first wanted to figure out when did we taste off flavors. Then we wanted to do our more comprehensive GC-GC technique to look at secondary metabolites, and then figure out if we can do some kind of sensor. So this is where we get into triangle taste tests. Initially, we actually thought that we could just spike in ethanol and that would lead to the off flavors. It turns out off flavor is a lot more complicated than just ethanol. And when we spiked in ethanol, we really didn't see a difference. Maybe that's because we used a bunch of alcoholics to do the taste test. I don't know. But basically what we did with this triangle taste test is we had our control and our fermented group. So we would just place our fruit into a chamber where we could purge it with nitrogen. We would monitor it to make sure that there's really no oxygen in there so that it starts to force it to go anaerobic. And then at predetermined time intervals, we would take these out and then give them as a triangle taste test to 11 or so participants. We chose 11 because this was during COVID and that's how many people were in the building. So this is some of the results that we got. And what you can see is that there really wasn't much of a difference going from, a few hours until we start to see maybe at 24 hours, people could maybe tell the difference here. And so this was starting to figure out what our thresholds were going to be for determining off-flavor production. So our analytical testing, what we could do here was we would sample our mangoes in the Netherlands, actually. So we took our TD tubes there, collected our volatiles, and then flew them back down to California where we could actually run them on our instrument and kind of produce our results. And what we see is when we kind of classify these based on amount of time in nitrogen, we see something here where we have like about a day and then more than a day, they start to really break apart and you can really taste the off flavors. Tasted a lot of bad mangoes. And so this is what the volatile profile looks like. So this is interesting because we can now look at what is leading and what are these secondary metabolites. This is one where we do see a clear difference between the two. And we can start to point out these different compounds. And what we see is that we have a lot of ethyl-derived compounds. And this matches very well with what you see in literature. It's the formation of ethanol, and then now you have ethyl-derived compounds that lead to this off flavor. But it's the combination of all of these together that really give the bad flavor. And so now it's kind of looking at how we can model and maybe use sensors. So the idea here is that we have like our initial measurement group. We can have one that goes towards natural aging, one that goes in this forced anaerobic. And then we do our TD sampling. We have an ethanol sensor, and then we also used our electronic nose, basically hitting whatever we had with it. And then we can use different conditions such as controlled atmosphere, cold storage, also our treatment strengths to as unknowns to figure out what's going on. And what was really neat with using the thermal absorption is that we could start to model this fermentation route as well as the ambient aging, and use these gray dots as our unknowns and kind of really figure out what conditions lead towards fermentation and what goes towards the ambient aging. And it's really good for us because now it really helps us make a more reliable product so that we have really good tasting mangoes as much as possible. So the final application is looking at produce quality. So we're really looking at native infections in mandarins. And the reason why is that the EU is starting to reduce its MRL limits of imazalil. So imazalil is used, it's a really effective fungicide for citrus to reduce any kind of mold. But it's potentially harmful. And so the EU is really becoming a lot more strict on how much there can be present. So we thought, well, maybe we can understand the incoming fruit and maybe we can prescribe different strengths of imazalil, or maybe there's something else that can be used. And so what we used here was our GC GC-TOF with thermal desorption, and also a new sensor that was using soft ionization chemical reaction and transfer mass spectrometry. So this is more like an electronic nose for mass that uses a mass spec. So first we prepared our fruits. So this is our infection of mandarins. So we would wound the fruit and put in some spores, store them in a bin, basically that had high humidity so that it would really promote mold growth. And then we would take photos kind of along the way. So you would end up with a whole bunch of really gnarly looking fruit. But we could take But what we really wanted to see, is when it was not so gross. And we could use UV light, which is one way to look at mold. This spot here is actually not a piece of produce. It was just a really dirty tray. But this is what you would see as it would come up. And so we took our mandarins and rigged up something so that we could just kind of collect the volatiles. So we would just purge with nitrogen for about a half an hour and collect on 10x tubes and then run them on our GC-GC. At the same time, we would do SPME along with the secret kind of electronic nose for mass spec. And some of the results that we got were really cool. We started to see classification or discrimination or distinction between our untreated and infected group within 1 day of infection. And so you don't see any of this mold actually becoming present. And these are fruit that I would definitely eat, but you start to see that there is a volatile difference. And as the infection kind of grows and grows, you start to see more and more groupings and larger differences. What we also could do was be able to model how this actually occurs. And so we would go from, initial time to 1 day, 2 day, 3 day, and we could see what happens to these volatiles as the infection increases. And so if we look at our chromatogram, we have, this is 1 day, and the bottom is 4 days post infection, and we can hone in on this guy here, and it comes up with it matches to a 3-methylfuran compound, and when we look at this, it's maybe a potential degradation product of isoprene. Isoprene in plants is emitted to combat abiotic stress, and so it really leads us to okay, we are along the right track here, and what we can do is we really see this start to increase over time. We use volcano plots a lot to figure out differences between these two groups, to figure out what's upregulated and what's downregulated. Look at, we can go back to our chromatogram, identify compounds of interest, and when we look back into literature, what these compounds actually do, we see that this one is emitted in fungi, but only detectable within the first days of growth. And this is what we see in our box plot too, is, our abundance is high initially and then drops way off. So, can we start to use something like this in our sensor development? And that's where we went into this soft ionization chemical reaction and transfer mass spectrometry. So, this is just an adapter that fits onto our Zevo TQD, and it draws in the volatiles using just the natural vacuum of the mass spec. And you can really just put your piece of fruit right in front, and you start to see its mass spectra. What we ultimately did is you can actually put SPME adapter on top, and so we use SPME to do some of this work. And this is what it looks like, just headspace of the fruit in a jar, and we inject this right into our mass spec. You get an immediate response, and you can see the different mass spectra of your control and infected. We really aren't great with, or I'm not great with, software and PCA, so we converted this and used the Chrome Compare Plus so that we could actually use the different, do the PCA so that we can group these. And we see really good groups of infection and non-infection after 1 day. Then we thought, well, can we determine different types of mold? And so common in mandarins are the colors, blue, green, and gray mold. And we were able to infect our mandarins and start to use our SPME secret to actually determine these different types of mold. So there is a ton of differences just in the volatile profile with these molds. And here's where we really started with the sensor. And then now we're using our GC-GC with tandem ionization to really go back to figure out what some of these masses are. And so when we look, we can pick out some different spots here. We have a really strong signal at 135 at our 16 electron volts. And this is one of the really important compounds that we saw from the PCA in the secret. So this is really helping us figure out what we actually just saw with the electronic mouse. And so that's basically a few of the applications that we've been using GC-GC with at Apeel. It spans across all different areas within the business. It's our first measurement in product development. And we really just kind of kept with this universal setup using the non-polar polar column choice. Also, volatile measurement is just proving to be very useful in assessing quality fruit, and GC-GC has really enabled us to understand a lot more of what is actually going on. So with that, I will thank tons of people here who have helped along the way, and thank you all.